What protects us from the harsh environment of space? The atmosphere does, but have you ever wondered what it is and how it functions? Well, in this video, we'll discuss all of that. So to begin with, what is it? The atmosphere is a layer of gas that stretches from the surface of Earth to space. There is no exact boundary, it just keeps getting less and less dense until it blends into space. One common convention, however, for such a boundary is 100 kilometers above mean sea level, the Kármán line. The atmosphere is divided into 5 distinct layers: the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. These layers are defined and characterized by their vertical temperature profile, essentially how temperature changes within them with increased altitude. The two layers that will be of interest to us in this video are the troposphere and the stratosphere. The troposphere is the layer closest to the surface of the Earth and rises to a global mean altitude of about 11 kilometers. The depth of this layer is relatively thin, however it contains approximately 80% of the total overall mass of the atmosphere. Temperature in the troposphere decreases with altitude, contrasting considerably between the lower and upper portions. Temperature in this particular layer is controlled by a wide variety of factors, including latitude, season, and locations distant from the ocean, just to name a few. Atmospheric scientists, however, use a concept called a standard atmosphere to represent an average atmosphere. Temperature in this layer decreases, on average, at a rate of 6.5 degrees Celsius per kilometer. Side note, the rate at which temperature increases, decreases, or remains constant on average is normally called the normal lapse rate. The normal lapse rate with the troposphere would therefore be 6.5 degrees Celsius per kilometer, as temperature decreases corresponds to a positive normal lapse rate. From about 11 kilometers to about 32 kilometers, the temperature remains approximately constant. Strangely, however, the temperature starts to increase about 32 kilometers above the surface of the Earth. The normal lapse rate of the stratosphere is approximately -1 degrees Celsius per kilometer. This is due to a layer of ozone that can be found at this altitude. The ozone molecules in this layer absorb high-energy ultraviolet electromagnetic radiation from the sun, which by extension warms the atmosphere in this layer. This is the stratosphere, and while it is often considered to be a rather dull and unimportant layer by some atmospheric scientists and meteorologists, recent research has shown that the stratosphere can have a large influence on surface weather. As mentioned previously, the International Standard Atmosphere is used to represent an average atmosphere. It is known as a static atmospheric model of how temperature, pressure, and atmospheric density changes over a wide range of altitudes. A static atmospheric model is one that doesn't change with respect to time. It has been established as a common reference for temperature. The International Standard Atmosphere is fundamentally a mathematical model, which assumes a linear distribution of temperature against altitude. The two other quantities, pressure and atmospheric density, are derived using this information and by assuming the atmosphere is in hydrostatic balance, which basically means that the wind in the vertical direction is not accelerating, and the atmosphere is obeying the ideal gas law. This is done using the barometric formula for pressure. Derivation is quite frankly out of the scope of this video, however a quick animation of the derivation will be shown on screen for those who are interested. Fundamentally, however, this model shows that pressure decreases exponentially with altitude, as evident by the exponential term in the equation. As pressure decreases, the air also becomes less dense, but the atmospheric density decreases, as described by the ideal gas law. This is the equivalent of being at a higher altitude and is often referred as the density altitude. Differences in air density caused by changes in temperature result in a change in pressure. This in turn creates motion in the atmosphere, both vertically and horizontally, in the forms of currents and winds. The atmosphere is almost constantly in motion as it strives to reach equilibrium. These air movements set up chain reactions that cause a continuing variety in the weather. The International Standard Atmosphere has a wide variety of applications, particularly in relation to aviation. Aviation standards and flying rules are based on the International Standard Atmosphere. Airspeed indicators are calibrated under the assumption that they are operating at sea level, where the atmospheric density is approximately 1.225 kilograms per meters cubed under this model. It also allows for a reproducible engineering reference for calculation and testing of engine and vehicle performance at various altitudes. The density altitude is used to assess an aircraft's aerodynamic performance under certain weather conditions. The lift generated by the aircraft's wings and the relationship between its indicated airspeed and its true airspeed are also subject to air density changes. Furthermore, the power delivered by the aircraft's engine is affected by the density and composition of the atmosphere. Thank you for watching this video. If you liked it, leave a like, and if you have any constructive feedback, drop it in the comments section below. To learn more about the atmosphere and atmospheric physics, I'd highly recommend subscribing to the YouTuber Simon Clark. A card to do this should appear on screen now. For references, please see the description below. Thank you once again, and goodbye.